first thing, a very basic level, you want to introduce machine learning. So real quick, we are assuming that you're at least somewhat familiar with ENVI, because this is a webinar about ENVI. So we're not going to go into all the details and background of what ENVI does. And so we're just going to start with machine learning. So the way I really think about machine learning is they're a broad class of algorithms that you give them data and you tell the algorithm what it's supposed to give you as an output. And the algorithm itself has to go through and figure out how to accomplish what you've tasked it with. And, you know, machine learning, there's a lot of different subsets, types of algorithms. But at the end of the day, you know, we're not talking about Terminator, no Skynet here taking over the world. Whereas if you get into things like deep learning, that gets a little bit more like artificial intelligence. And so for those that don't know, we currently have a module for ENVI called the ENVI Deep Learning module, where we package in object detection and segmentation using UNets. And you can see some of the high-level capabilities and feature functionality here. So apart from that, we have had over the years, I think it was maybe 4 or 5 years ago, we added some basic machine learning tools to ENVI. And, you know, we realized at a later point in time that they weren't the most user-friendly. And we thought it really made sense for us to circle around and revisit machine learning capabilities within ENVI, which brings us to where we are today. So with that, and before we get into the tools, I want to make sure we spend a little bit of time talking about hardware requirements and how you'll be able to get and access the tools for machine learning. So because we have machine learning and deep learning in ENVI, we want to make sure to spend time talking about hardware and how to access. So the machine learning tools are going to be free. You will not need a license of any additional module. However, they are packaged with the deep learning module. So the next slide shows the workflow for how you'll be able to, once you've installed ENVI 5.6.3, get the installer and install it. But the tools for machine learning are packaged with the deep learning installer. But like I said, you don't need an extra license. You do not need to purchase deep learning. If you want to use any of the deep learning algorithms, you'll have to purchase deep learning itself. And some important distinctions here, machine learning just uses the CPU. It does not require a GPU, versus deep learning does require a GPU. So we'll talk about this a little bit more if we've got time. The CPUs that we recommend for use with machine learning are Intel. That's because there's some Intel optimized libraries that have significant performance improvements for a handful of algorithms. We'll talk about that a little bit later. So just to show you what this will look like. So once ENVI 5.6.3 is released later this month, the ENVI Deep Learning 2.0 is also going to be released at the same time. And so from within ENVI, you'll have a new folder called Machine Learning. If you click on the Install Machine Learning Toolbox entry, you'll have the little dialog that appears in the lower left. Once you click on Download Installer from that dialog, it'll take you to our Download and Licensing portal, where you'll see ENVI Deep Learning 2.0 listed as one of the installers that's available to you. Download, install it. Like I said, it's free, does not require a license of deep learning in order to access any of the machine learning capabilities. So just a reminder, these will both be released later this month. So we're slated for the last week of October, assuming everything goes well with our candidate testing and release process, which we're getting started here this week or early next week. So TBD, we do have a few weeks before this comes out. All right, now that that's out of the way, let's jump into some of the features and functionality. So at a very high level, here's an overview of the different types of algorithms and algorithms that are included with the machine learning tools. We have 3 separate classes where we have supervised classification, where you have an input raster in geometry that represents pixels or features of interest, and you're going to go through and map where similar pixels are located. So if you're familiar with traditional remote sensing algorithms and approaches, this is very similar to using a tool like Spectral Angle Mapper with a few key differences, which we'll cover. Anomaly detection, these are a new class of algorithms that we're adding to ENVI, where we have, so it's anomaly detection that works where you train these machine learning algorithms on normal data, And when these algorithms see something that's different, it will give you a binary 1-0 flag if it's anomalous or close to our data that we were originally trained on. Lastly, we have a handful of unsupervised algorithms. These are algorithms where you just give it an image, no labels, no training data, and they're effectively clustering algorithms that separate your data into X number of bins. So if you used ISO data classification before in ENVI, or k-means that we've had in ENVI, behaves exactly the same. We're just going to have a machine learning version of it. So one of the things I want to make sure to call out here is you'll see that for the supervised and unsupervised algorithms, I put stars next to each algorithm. So this is kind of the Zach approved list, but feel free to use any of them, no matter how you want. So if you're using supervised classification, I really recommend using random forest or extra trees. Extra trees is very similar to random forest. It's a little bit extra random. I do not recommend using SVM, mostly for my notes there, because it is very, very slow. So I've got a table that's later in the slides that will show you just how slow it is compared to random forest and some of the other machine learning alternatives, which are much, much faster and give you a better user experience. So just a little bit of food for thought, trying to help you give you a direction to go in. If you're new to machine learning, by all means, feel free to use whichever algorithm you'd really like. All right, let's go ahead and jump into the tools that are going to be available once you install machine learning, and we're going to cover some of the use cases as well. So here I just kind of broke up the machine learning toolbox into 3 groups: quick access or top level tools. We have our one-shot or easy peasy classification tools in the middle, and there's a handful of training algorithms that are exposed directly. These are our training for unsupervised classifiers, which don't require any labels, and it's very easy to do just on your own. If you do want to train models, we have a couple of different tools that allow you to do that. We'll talk about that here in just a second. So the 3 different sets of tools that we've got as part of this are our easy peasy one-shot classifier tools, where we're trying to find more pixels like my examples. We have a raster and ENVI regions of interest, and you get a classification image as your output. So here, all of our easy peasy tools are bucketed and shown in the screenshot on the left. If you don't have labels already, or you have more than one image and more than one image with training data, there's 2 different tools that you can use to generate a classifier. You can either use the labeling tool in the middle, which has a little bit of hand holding for you, also helps out with data management and automates training data preparation and makes it very easy to generate a classifier, machine learning classifier, with the click of a button. So in addition to that, well, let me pause there. We'll get to that in a second. Lastly, we have our freeform, which allows you to use the ENVI modeler or the ENVI API from IDL to also create a customized machine learning workflow. So as I like to call them, they're little spaceships. I always like to make my ENVI modeler files look like spaceships because, why not? I'm still a child at heart. So with that, let's have a little bit of a closer look, and we'll show this live, well, not live, a video of this in action here in just a few minutes, where for our easy peasy tools, if we're looking at random forest, for example, we specify our raster and ROIs. We'll talk about what background labels is here in a minute. Then we have some model specific parameters shown in the green box in the lower left. And then we specify the output file. So these are really just meant to be quick and dirty, really easy to use. You don't have to spend much time on them. I don't ever even tweak the default parameters because they work very good. So this is our easy peasy classification tools. We'll show that a little bit more. Here we have a quick video showing machine learning labeling tool. And let me pause this so I can show some of the features. So sorry, this is a little bit small. It was bigger before I was presenting. Well, I thought it would be easier to read, but it's not. So in the video over on the right here, this is just showing our training dialog within the labeling tool. And this is a drop-down list that shows you all of the different types of algorithms for supervised classification. So it makes it really easy for you to switch back and forth between different types of machine learning classifiers, generate them, and you can go and process imagery and determine which one is best. But one thing I want to call out that within the labeling tool, there's actually 4 types of projects. Pixel segmentation and object detection are both for deep learning. So you won't be able to do anything with your data and labels there unless you have the deep learning module to be able to actually generate the classifier. So supervised classification and anomaly detection are machine learning based, and there's a little tooltip that appears which will let you know that. And then lastly, our other way that you can use the machine learning tools is through the ENVI modeler. We'll show this here in just a second, but all of those easy peasy one-shot tools have this nice little button that says open in modeler. If you click on that dialog, it opens up the ENVI modeler, which you can then copy and paste the workflow from, customize it, tweak it to meet your needs. So with that, let's jump into our scenario and start to run through some of the details about how you get your data ready and what training data looks like. So data credits for this, we've got a worldview data set. We are using 8 bands, so that covers our visual and near infrared spectrum. So with this scenario, what we're going to be doing is we're going to find where there's the hot or molten lava, which shows up nice and orange on the right. We're going to find older lava flows that are cooled off, which is the really dark black color in the right and the left. And then we're going to try to extract the volcanic gas plume. So for our scenario, and these steps are automated for you when you're using the easy peasy tools. For any machine learning workflow, even deep learning, you have your training data, then you make your classifier, and then you actually classify your image. So we're going to very quickly walk through what these look like if you're manually clicking buttons, but the videos that we'll show are not going through these steps because it's automated for you in most of the tools that people will likely use. So before we get to training data, it's important for us to take a step back and talk about what you really need to do to get your data ready for analysis and ready for use with machine learning. So from a remote sensing perspective, the standard that, the industry standard, I guess I would say, is that your data is processed in units of surface reflectance, where a pixel value of 0 is going to represent 0% reflectance, so pitch black. And most commonly, a pixel value of 10,000 represents 100% surface reflectance. So there's a little trick here where we use unsigned integer instead of floating point to reduce our file sizes, but 0 to 10,000 is a pretty common range that you'll find. So we've processed our worldview image here using QAC, which is quick atmospheric correction, which gives us an image between 0 and 10,000, which corresponds to 0 and 100% surface reflectance. Now, there are some additional tools as part of the machine learning capabilities that allow you to use radiance data if you want to, where you can automatically determine those normalization ranges on your own. So that's the pattern that we like to lead with. But if your data is a little bit different, we have some tools to help you out. So let's talk a little bit about what's actually used for training and what our training data looks like. So when we're using machine learning, especially if you're familiar with deep learning, for machine learning, we're not doing anything that let me rephrase that. With machine learning, we're just using a single pixel as our training data. For people who have used ENVI before, we have some spectral profiles with a handful of pixels from each of our 3 classes, just to give you an idea of what the spectra look like for each of them. The difference between machine learning and deep learning from a training data perspective is machine learning, we just have to identify some examples or pixels that represent features we're interested in. Deep learning can be a lot more involved to actually label your data, where you might need to make a perfect mask that would represent, where our gas plume or hot lava or cooled or previous lava flows are actually located. So it's very easy and very quick and rapid to label data for machine learning. The other thing I want to call out is that for machine learning, you can use any number of bands. You can mix and match different types of data as long as they have comparable data ranges. Normalization is key. So if you're stacking, say, a spectral index on top of your, spectral data, you want to make sure they both go from, 0 to 10,000 or, lower value, upper value, just to make sure that it's consistent, apples to apples. So to give you an idea, getting ahead of myself there. So one other very important concept with machine learning is background data. So if you're familiar with the ENVI deep learning module, if you're using object detection or segmentation, which are our UNet architectures, any data that you don't label is automatically assumed to be background data. With machine learning, just like deep learning, you always have to associate a pixel with a class, meaning that if you're not doing something like land cover classification, you're going to need to take a few minutes and specify a few examples of things that you're not interested in. So for example, like the screenshot shows on the right there, we have a cloud with a dark green outline, which represents our foreground. And then everything else is our background, things that we don't want to identify. So with machine learning, that means you'll probably go through and identify and draw some regions of interest around forest, bare earth, man-made, water, anything that doesn't really fit in with the targets that you're looking for. And so for our example, with our volcano, here's what our training data actually looks like. So first, starting with our kind of orange, which these are pretty small polygons, but if you look in the top left of our screenshot of ENVI, you can see where we've got our active lava flows labeled. We have our gas plume as this kind of indigo purplish color, and then we have our cooled previous lava flows as blue. Red represents our background data. So just like I described for our example with clouds, we want to make sure to give machine learning some context for what we're interested in versus what we're not. So we have a handful of urban pixels identified in the top left of ENVI's display. We have a few examples of bare earth, some vegetation, water, a couple of places where we have our shoreline or white caps from water meeting the shore. And we also identify clouds as things we want machine learning to ignore because our clouds are hopefully different from our volcanic gas plume. So there's just kind of an example trying to tie together how background data comes in to the training process for machine learning. And with that, let's jump through exactly what the three tools would look like. So sorry, let me take a step back. So in the slide I showed just a minute ago, we had our 3 steps. We're going to generate or extract our training data, generate our classifier, and then classify our image. Here, when we're extracting our spectra, our training data from regions of interest, we specify our image and our ROIs. And this is also where normalization information comes in. So just like we talked about, our image ranges from 0% reflectance with a pixel value of 0 and 100% surface reflectance with a pixel value of 10,000. So that's our range for normalization. Like I said earlier, if you don't know this, you can actually click on this handy little button, which will pop open a calculator. You can specify some images and it will auto-populate those fields for you. That means that you can use data with surface reflectance or any other style of data, and it should hopefully work. The next step is training. I'm not going to spend much time on this because it's pretty straightforward. You specify the training data that you generated, can optionally tweak some of your model parameters, and then generate your model. And then our last step is classification. So for classification, you'll specify the raster to process, the previously generated model, and optionally normalization information. So 2 things that are important to call out here. The normalization information when you're classifying an image is optional. That's because we store the normalization information from your training data, because our assumption there is that the data you're processing is similar to the data that you were training on. So you don't need to specify normalization here. You can if you want to. You still have that little calculator button to have access to auto-calculate that for you if you need it. In addition to this, the other important point is that the models that are generated for machine learning are just JSON files. So that means that it's human readable. You can open up in a text editor, use VS Code for some nice fancy syntax highlighting. And we'll talk about that a little bit more in just a second. But very quickly, those are our 3 steps for generating a machine learning classifier. And like I said before, we actually don't need to manually go through all those steps, because if we're using our easy peasy training tools, this will be automated for us. So this video shows selecting our image, picking our training data, and using that one-shot easy peasy classification tool for random forest. This part of the video is sped up because it takes a couple of minutes to actually process the whole scene. And then here we have our results. So I'm going to let that play once more, and then I'm going to try to pause it at the very end. So we'll see what our results look like. So pick your image, pick your data, hit go. And once it's finished, we'll have this pop up in the display and we'll pause. So I probably spent 2 or 3 minutes drawing some of those regions of interest. So with only spending a few minutes of time and effort, we can pretty easily map where pixels are located in the rest of our scene. So it's very quick, very easy to use machine learning, completely different from deep learning. Not that deep learning is hard and scary, but it's just more work. It's a little bit more complicated and different. So is this a perfect result? No, and you're not going to get a perfect result with deep learning either, but with how quick and easy it was to generate, you could go through with some classification cleanup, or use the edit classification image tool in ENVI to fine tune your results here. So one thing that I want to make sure to call out, remembering the variety of classes or variety of pixels that we indicated were background with our urban, forest, water, and clouds, you can see that we have, there's maybe a few areas of confusion around the coastline. Not sure if that's exactly where the water is, there's white caps, or if maybe it's just old, previously exposed lava flows that you're seeing. So that's where background data comes in to help make sure that we're focused on the things we care about and not things that we don't care about. Our second video here that we're going to show, let me get to the next page here, is using the ENVI modeler. So let me pause our video real quick. So if you open up one of our easy peasy tools, for example, here we have random forest classification. There's that open in modeler button in the lower right of the dialog. If you select that button, it then opens up the ENVI modeler with the workflow that actually runs behind the scenes. And here, once you have this open, you can copy and paste, customize it to do exactly what you need. So for me, what I did was I took our 3 steps where we have extract training data from regions of interest, generate our classifier, and classify our image. And then for this ENVI modeler workflow, when we actually run it, and this is live, no speeding up through the process, we can run our ENVI modeler workflow in debug mode, which allows us to see the time it takes to execute each step. Also gives us a nice visual so that we can see how much is done and how much is still needs to be finished. But all in all, this takes about 25 seconds to finish, takes about 5 seconds to get our training data from our regions of interest, 10 seconds to generate our random forest classifier, and 10 seconds to classify the subset of our image. So I wanted to make sure to show that in real time, because it's very quick and fast and easy to use these machine learning algorithms. And because it is so fast, it's easy to go back, maybe tweak your training data a little bit, add some examples for false positives or where there's confusion between your classes, and iterate. And the benefit of machine learning versus deep learning is you can do that in a matter of minutes rather than having to wait hours or days because it takes so long to train. So, all right, quick little time check here. So I think we've got enough time. I'll be able to get through the rest of the slides and have some room for questions. So with that, let's talk a little bit about the model files that are generated from machine learning. So I'm not going to go through all the details, but the highlights are the model file is just JSON. It's something you can open up, edit, and read if you want to. So if you want to change the colors or maybe the class names, you have access to do so. Please do beware though, if you make a syntax error in the JSON file, we're not going to be able to open it up. So it is kind of an edit at your own risk, but you have the information and you can change it if you need to. There's two important things that the model files contain. First one is the report, which gives you a precision, accuracy, recall, and F1 score for each class that's actually a part of your model. And then you have a human readable confusion matrix. If you've never worked with confusion matrices before, I like to think of them as being appropriately named, because not only are they do they help you understand what classes are confused with one another, they are confusing in and of themselves. So the important thing to know is that you want all of the numbers in a confusion matrix to be along the diagonal. The diagonal represents correctly identified pixels. Anything that's off the diagonal is going to be pixels that were supposed to be classified as one class and they were identified as something else. So here we have about 750,000 pixels, and there's a grand total of, I think, 14 pixels that are classified incorrectly from our training data. So machine learning typically does a very good job on the training data that you provide. For me personally, when it comes down to evaluating the performance of a machine learning algorithm, I like to actually look at an image, classify a data set that I was not training on, and evaluate the performance for myself. That's really where I think the rubber meets the road with this, because for machine learning, you shouldn't be using just tens and tens of millions of pixels as examples. Ideally, you probably want to keep it, less than 5 million, maybe 2 million at most. I like to think of quality over quantity. And when I say quality over quantity for samples, I mean, rather than getting many, many examples of water from one image, it's probably going to be a better idea to get 10 or 15 different examples of water from 10 or 15 images and have, 10, 20, 30, maybe 100,000 pixels total that you're using as examples. So something that you can feel free to play around with, but with machine learning, it's quality, not quantity, and deep learning, it's a little bit of both. So, all right, last big feature I want to make sure to call out is you can also use spectral libraries with machine learning. Now, before we get into the details, I really want to call out, this is fully featured, it works, but it is also our first pass. I'm sure that there's some slightly different use cases that are not covered here. So if you are playing around with machine learning and spectral libraries, if things aren't working quite like you expect, or you have some other ideas or concepts, feel free to reach out and let us know. But at a high level, how this works is when you're getting training data from a spectral library, there's two things that you need to know. You need to have a raster with wavelength information, which indicates what we are resampling our spectral library to. So for example, if I'm working with an 8-band worldview image and I have a spectral library with 1,000 samples, we need to make those 1,000 samples into 8 and at the right wavelengths to match our raster. So that's why it might seem silly if you have to pick a spectral library and a raster, but that makes sure that we can combine the training data from spectral libraries and regions of interest in one. Second important thing here is that the spectra names for the targets that you're looking for, you can use asterisks or wildcards in the names. So for example, if you are using a spectrometer in a lab, you have 500, 1,000 measurements of what a specific mineral looks like or material. As long as you have nice names for all of those spectra, you could, like we've got here, oak, water, or grass with asterisks on either side. And then it will pull out all of those examples from the spectral library and combine them together. Because really, you don't have 500 or 1,000 or 2,000 separate spectra for different things. They're all the same example. So last thing I want to quickly show here is that you are able to use the output from spectral libraries and regions of interest together. So like I said, that's part of why you have a raster. That's an input to when you're generating training data from a spectral library. That way we can make sure that the training data has the same number of bands, wavelengths, as the rasters that you're actually going to be processing. So this is just a reference example to show you how you would bring these two together, where we have ROIs, a raster that's used for getting training data from ROIs and the spectral library. So like I said, if you've got other use cases or examples, feel free to reach out and let us know. All right, so with that, we do have a little bit of time to walk through some of our extra slides here. So first one that I want to spend a little bit of time on is our Intel optimizations. So as I said before, on the first slide when we're talking about our algorithms, Zach does not like SVM, and it's specifically because of this slide right here. SVM takes dramatically longer to go through and generate a classifier for training and actually classifying an image. If you're looking at this table here, it actually took so long to classify an image, we just made up 15,000 seconds for how long it took because the process never actually finished. So it's an extremely slow process. So without Intel CPUs, you're not going to have a great user experience with SVM or nearest neighbors. Now I'm calling this out because I want to accentuate and make sure you have a good user experience. You'll see random forest compared to SVM for training and classification time, which is, faster for both scenarios. So that's part of why I recommend random forest. That way you can very quickly see your results and iterate if you need to, and help save you time from end-to-end, your end-to-end workflow. So couple of other things to spend a little bit of time on here. So a slide just to talk about machine learning compared to deep learning, if you are familiar with both. Machine learning, I really think of as very easy to use. Draw a few bounding boxes or polygons, and just like we showed with those easy peasy tools, pick your raster, pick your ROIs and hit go. And that can take as little as 30 or 45 seconds, depending on how big your data is, how many examples you have. And along those same lines with machine learning and deep learning, you really don't have to do tons of data management with machine learning. It still gets in there a little bit, especially if you have, 30 or 40 images, you're trying to do land cover classification, but not quite as much data as if you're working with deep learning. Additionally, for machine learning, we're actually training on the CPU. Just another reminder, we're not using the GPU like deep learning does. So for ENVI deep learning, as a reminder, we only use the GPU for training, and for machine learning and ENVI, we only use the CPU. We talked a little bit about training data already. Like I said, it's about quality, not the quantity of pixels that you identify. Don't go, if you have half of your scene is water, don't draw a region of interest that covers half of your scene as examples for water. Start small and grow from there. When I say start small, you can have classifiers that you train with as few as 10, 20, 30,000 pixel examples of your features of interest. Start small and grow. That's a good rule of thumb for machine learning and deep learning. So that's all I want to say there. We could probably talk about that for quite a bit. Last thing I want to call out here, and who you talk to, this might change a little bit, but I just wanted to make sure to call out some of the differences between like traditional remote sensing algorithms and machine learning. So there's a couple of examples of algorithms at the top on both sides just to help you get your bearings if you're not familiar with traditional remote sensing practices. Some of the things that I like with machine learning compared to traditional. So with traditional algorithms, you usually have custom parameters or thresholds that you have to set to really fine tune the output that's generated. With machine learning, you don't usually have to fiddle around with parameters at all. The default parameters work pretty good for most scenarios. The big difference is that with traditional algorithms, you can specify one example or two examples from a spectral library, whereas with machine learning, like we talked about, you have to have foreground and background examples. So you have to use more than just one example of your feature. So that's one of the big differences. So machine learning doesn't solve all problems with spectral classification. Sometimes you will still need to use traditional approaches when you just have spectral libraries for an image or specific material, mineral, whatever it is that you're looking for. Let's see here. So I think that's kind of the highlights from here. we're going to pivot a little bit to talking about a few examples, and then we'll open it up for questions. So I'm going to go through some of these pretty quick. You will get a copy of the slides to look at them more later. But first example here is land cover classification using PlanetScope data. For this, I used about 30 images, and I had a handful of very small regions of interest for different types of land cover from each of those images, just kind of scattered around the world, and different sensors, different times of year, things like that. So one thing I do want to call out is that when you are using machine learning, there is going to be a limit for your performance. You know, machine learning is not going to solve all your problems, just like deep learning won't solve all your problems either. So one of the nice concepts here is that you can use machine learning as a starting point, create a basic land cover classification model, and you can actually use the outputs from machine learning as automatically generated labels for deep learning. So you can directly take the results from machine learning, grab your input data and the classification image, and generate a model with deep learning. So it's a really nice happy path to go from one to the other if machine learning is not quite meeting your needs, or you don't have as many bands as you might need to differentiate between types of materials and features. Lastly, I just want to show one example of unsupervised classification. This is really just a pretty picture. We just have 3 classes here where we've got water, kind of barren, or what I call sparse vegetation, you know, most likely grasses. And then we've got forest as well. So also, like I said, nice colors here to look at. As we said already, you can use hyperspectral data with machine learning. In this example, I was trying to delineate between different kinds of trees that were shedding their leaves at different times. So looking at green, yellow, and red trees. Yellow is kind of hard to see, but the green trees and red trees pop out very well. Here we have an example using anomaly detection. So this is just kind of a nice concept for how anomaly detection can work, where we train an anomaly detection classifier on water, and then when we see something that doesn't look like water, it comes out as an anomaly and looks red like we see here. Now, this image isn't perfect, and it's not supposed to be. It's trying to show you one of the most simple, basic use cases for anomaly detection. With a little bit of classification aggregation or classification smoothing, you could remove almost all the noise, and then you pretty much have a map of things that are man-made, land, or ships for your scene. For a slightly more interesting example, using anomaly detection here with Worldview 3 SWIR data, we can go through and we can train an anomaly detector on what pixels look like that are not actively burning. So then when we see pixels that are hot, where there's a wildfire, so this is from the Black Fire in New Mexico, we can actually identify those with anomaly detection. And just to call out, you could probably use supervised classification as well, where you could identify manually, here's areas where there's fires burning, but this is just another use case for anomaly detection. And last but not least, I want to show a example where we can manually go through using PlanetScope data for change detection. And let me make sure to pause here so you can see. So on the left, we have time 1, which is pre-fire. On the right, we have time 2, which is post-fire. And you can see this very sharp line, this distinction between where the fire burned in this area and where it didn't. So the yellow boxes represent areas that have changed, and red represents areas that have not changed. So for this example, I actually took time 1 and time 2 PlanetScope data. I stacked them together. So we have 8 bands, and we can very quickly, I mean, you see I have 6 boxes. It took me maybe 20 seconds to draw these. And then we can use our easy peasy machine learning algorithm or machine learning tools, which will generate a classifier and classify our image for us. So this is also a real-time video. So there's like 15 seconds where it's not very exciting in here. And then it'll show the results here. So actually, I'm going to skip ahead and pause just so you can see it. So worked very, very well. And like I said, with anomaly detection, you could go through with classification smoothing or aggregation and very easily fill in the gaps on the right and remove some of the spurious noise on the left. Or because it is so quick and easy, you can fine tune, add some more examples to your training data to delineate between these two different classes. Okay, so with that, let's turn it over to JP again, and we'll go through a couple of questions. We might run a few minutes over, just a little heads up. So JP, over to you.
Fantastic. Thank you, Zach, for showing us how to take ENVI to the next level with machine learning. Yeah, at this point, we will answer some of the questions that have come in. David asked, check this out, Zach. David asked, when you're analyzing time series, which is one of the last examples that you have with machine learning or deep learning methods, can you leverage the spectral changes of things like growing vegetation to improve classification?
Yeah, absolutely. So one of the important concepts when you can think of imagery in general is, if you have a hyperspectral image that has, say, 100 or 200 bands, let's remember that at the end of the day, that's really just a signal. They're just data points that we're processing and analyzing. So you can use, like spectral indices, for example, with machine learning, picking spectral indices that make the features of interest that you're looking for pop out compared to everything else. And that's something that you could use with machine learning or deep learning. So I had a very basic example with change detection that I showed there at the end, but you could probably try playing around with a stack of 10, 15, or 20, spectral indices from like Landsat or Sentinel-2 imagery and see if you want to pop out, different types of growing seasons or something like that. So I haven't played around with it, but it is important to remember that as long as it's an image, you'll be able to use that with machine learning or deep learning. If you have more than probably 6 or 8 bands, I would recommend machine learning instead of deep learning. Machine learning is going to be a lot faster and easier to work with, and deep learning is not always appropriate to use when you have a lot of bands. And it goes a lot slower, a lot more data to process. So
great.
Back to you, JP.
Here's another question. We've been talking about spectral imagery, right? And the differences between deep learning and machine learning. Machine learning can accept those 100, 200, bands of hyperspectral data. But so then we say that machine learning is more spectral while deep learning is more spatial, a little bit of spectral, right? When we say spectral, do we really mean like signal? Like could it be like a like SAR or different modalities?
Yeah, exactly. So yeah, when I say spectral, I really mean signal, looking more at the just the values of data that are passed to it. When I say spatial, I really mean more context. So the deep learning algorithms that we have in ENVI deep learning are using convolutional neural networks, which pick up spatial context from not just a pixel you're looking at, but a window around it. So like our eyes do when we look at a feature and we see things around it, and we can make a better judgment for what we're actually looking at. So yeah, you could use other data modalities. That was actually a question that also came up this morning in the version of this webinar, excuse me, for Europe. And you could probably use SAR data. One of the things I was thinking about is, it probably depends on like how noisy the SAR data is, because your signal is going to have some variation or variability. But as long as your data is normalized, you could use elevation data. You could have time series. I don't know if it'd be looking for subsidence or landslides or whatever that might be, but you could do the same sort of thing with SAR. There's probably a lot of different ways to solve some of these problems. So
the possibilities are endless.
The possibilities are endless, JP.
All right, fantastic. Well, we are running up on time, so if you do have any burning questions, here's the contact page for either me or Zach. If you want to go ahead and send one of us an email, we'll get those questions answered. So we'll wrap things up. We appreciate everybody's attention on the line, and thank you again, Zach. Just a reminder that a recording of this webinar and the slides will be emailed to you next week. Thank you, everyone, and have a great rest of your day.